Today, Yulong from NVIDIA. So Dr. Cao is a research scientist in the NVIDIA Autonomous Vehicle Research Group. He got his PhD in University of Michigan from the group of Dr. Mao, and got his BS from Shanghai Jiaotong University. He has done a lot of research in vehicle security, autonomous vehicle security and safety. Today, his talk will be about the security, safety, and human-like autonomous driving. So, without further ado, let's welcome.
Yeah, thank you for the great introduction. My name is Yulong, and today I will present the talk towards secure, safe, and human-like autonomous driving. So before we begin, maybe a quick recap on how these classic autonomous driving systems or ADS looks like today. Usually it's a vehicle equipped with multiple sensors like LiDAR, camera, radar, and those sensor data will be processed by a sequential of modules, for example, perception for sensing ego and environment, and then prediction for obstacle, predicting future path, and planning module for planning out behaviors of ego future path, and eventually comes into this control module, which turns all the signal into concrete control signal passed to the vehicle to do braking or steering. In the autonomous driving field has been started back in 2004 from the DARPA Grand Challenge. It's already around like 21 years. And there has been great progress with this machine learning advancement. You can saw most of the modules like perception, prediction, and part of planning has been using machine learning algorithm or neural networks inside of those modules. And even more recently, there's a rising trending of using end-to-end ADS, which means there's like single machine learning model taking data from the sensors directly outputting planning trajectories. And this field has been pretty capital intensive. We have different companies, either vehicular manufacturers like GM, Toyota, or like EV companies, Tesla, or service provider, NVIDIA, Momenta, and even like government agency like DOT. However, what we saw today is that we do have some like achievement. For example, these ADAS or advanced driver assistance systems has been already widely used. If you have a recently bought a car, pretty much they will be equipped with one of these ALC, automatic lane centering functionality or adaptive cruise control, which can help you like alleviate some of the stress when you're driving on specific ODD, like on the highway. However, it's still not there for the level 4 autonomous driving, which doesn't require human intervention, which can drive in different ODD like highway or in the city. I feel like one analogy I really like is the technology we had on the autonomous driving systems. It's kind of like the AI programming tool, for example, Copilot. Sometimes it's a really useful tool, just like ADAS, but it's only used in certain ODD that you don't really care about the critical components. For example, if you're doing research, you want to write a very critical part of the code, you probably won't trust Copilot. So there's still some way to go for the fully autonomous level 4 driving. And one key like problem for why we haven't been there yet is the testing for these autonomous driving systems are really, really hard. And let's first take a look at how industry today are doing the testing. Usually there are two categories of testing, online testing and offline testing. So for online testing, usually it's called structured testing. Basically, like you will have a fleet of vehicles employed with sensors and potentially the autonomous driving systems you build and try to rolling out the policy on the road in the real world. Of course, you will have a safety driver too, just in case safety issues happen. And for the offline testing, basically you don't actually deploy the vehicle on the road, which can be more scalable. One way is to using this real world replay. Basically, you are collecting all this sensor data like GPS, camera data, LiDAR data when you do the structured testing. And you can store those data in your like cloud and rolling out your policy on those replays. And another way to do offline testing. To do offline testing is through simulation. For example, NVIDIA, we have this photorealistic simulator called DriveSim. Basically allows you to reproduce or simulate like a scenario to test your AV policy. And also we have like generative models these days to help to reconstruct different ODD. For example, these three, you can change the weather and also road conditions a lot. But even with all these different testing methods, it's still really hard for us to reaching a satisfactory point where we say, okay, it's safe enough and secure enough to rolling our system on the road. And I feel there's like two key reasons behind this. First thing is that we really only collected limited mileage and limited observations through all this testing. Even for like offline, like simulation, etc. It's due to first, you have a very semantic richness in the open world, real world setting. For example, on the right-hand side, you can see there are some examples from Tesla showing, for example, that one, you have a like container box towed by a trailer and the FSD cannot detect it. And on the right-hand side, it's a pedestrian balloon for Halloween. And there can be a lot of misdetection. Even for human, maybe sometimes you will detect as a pedestrian. And this is all due to the semantic richness from open world examples. And also if you like try to expand it a little bit to the temporal domain, for example, you have a driving scenarios with multiple agents interacting with each other, the things gets more complicated. For example, this is a clip where you're driving downtown Manhattan. You can hear the honking, but I guess you can feel the stress. But yeah, essentially, these are very challenging since we are going to deploy L4 in the real world, and we expect the system can handle all these open vocabulary scenarios and really hard to define behaviors. And another thing is that due to this unbalanced data, since we have this semantic richness, we really need all kinds of data to conquering these long tail scenarios. However, according to DOT, you only have like 124 accidents or 1.3 among them are fatal in like 100 million miles driving. But for the like field leader Waymo, they barely just reached this 100 million bar this year in July. And last year, they're only like 20 million miles of data driven. So you can see we really don't have many these long tail scenarios there. And it's also this year Waymo just like released this new data set for end-to-end driving and include some like long tail scenarios. So this is really some missing piece even in the research and also industry. So we start with that. I will kind of in this talk, I will briefly talking about some of the way to kind of speeding up the testing process. I propose to using adversary, which is attack sometimes, as an express way to stress test this system. And in the first part, I will briefly talking about this many attacks on the autonomous driving systems, including on perception, and trajectory prediction and planning. And on the second part, I will talk about how we in return using all these attack to improving the robustness of the driving system. And lastly, I will kind of trying to extend, since nowadays we're kind of getting into the era of foundation models. Everyone is using like ALM, VLM, automating tools. I will talk more about what we are going to expand into the foundation model era. Okay, and any questions so far? Feel free to interrupt me, and if you have any questions. Okay, then I will go ahead. So before we go into much details on the adversarial attacks on AV, a simple example for adversarial attacks. These are original brought up by Yan Gu fellow back in 2014. And the classic example is that for the image classification task, for example, you have a panda, you have a classifier that can detect that panda with 60% confidence. And this attack works by adding this perturbation in the middle, which is barely noticeable on the right-hand side. And this image will be fooling the classifier and detected as a gibbon. And how it works is also pretty straightforward. All you need is formulating the perturbation you want to add. For example, here, it's just like some random noise, like in the LP norm bounded domain. And all you need is a loss function as a target. For example, you want a target attack to be detected as a gibbon. And then you just solve an optimization problem in the third row. And you can calculate the perturbation, add it back to the original input, and you get the adversarial examples. And since like 2014, the paper and the submitted paper in this adversarial field has been exploded. This one is from Kalini, which is a kind of a legend in the adversarial machine learning domain. And you can see they stopped doing the survey, I think 23. But essentially, we have so many different categories of attack, for example, white box, black box, and different attack vectors. And there are different categories of attack, like membership, inference, privacy invasion, poisoning. And nowadays, for ALM, you have jailbreak, etc. However, originally, all those attacks are kind of limited to digital domain. And like you only consider a machine learning model, which is less realistic threat model. Not until like 2017 or 18, the first like physical attacks, which is pretty famous in the field, for the researcher trying to manipulate a stop sign, put some like graffiti on the stop sign and make it being detected as a speed limit sign. And furthermore, researchers are trying to push the boundaries even more to fooling the entire video detection model on these, so it can be consistently detected as a speed limit. However, as we shown at the very beginning, we know that nowadays, like autonomous driving systems or vehicles are equipped with multiple sensors. In the perception module, we have both camera-based perception and also LiDAR-based perception, which are usually considered more robust since it can natively capture the depth information. So the question at that time for us is that whether these LiDAR-based perception systems are actually also robust to this kind of attacks. And before we go into how we attack the LiDAR-based perception system, a little bit background on how a LiDAR system works is basically the LiDAR system will send out a light signal, and the signal will reflect it from the obstacles. And by calculating the time of flight, you can get a distance. And by scanning around, you can get a 3D depth information, just like a depth camera. And to attack it at that time, it's also very straightforward through this LiDAR spoofing attack. Basically, the attacker just need to take up a signal from the LiDAR system so you can sync with the LiDAR system and then relay a signal to the LiDAR, basically spoof a laser signal to the LiDAR such that you can spoof additional points. And by repeating this pattern, you can kind of spoofing multiple point cloud at the LiDAR system. And as a result, you can see on the left-hand side, you can pretty much spoof like a few points there. However, we found that it's by merely like doing this sensor spoofing attack, it's not capable of fooling the LiDAR-based perception system. Because, for example, on the left-hand side, you can saw the real reflection from a vehicle is pretty dense, consists of like hundreds of point cloud. However, with that current sensor spoofing attack capability, we are only can spoofing like tens of under like 60 points, and also it's pretty sparse. You don't get so much controllability on how the shape. But remember that we know that adversarial attack can generating adversarial examples that can exploit the machine learning models. So we kind of proposing, okay, we're just using the same sensor spoofing capability that cannot fool the LiDAR-based perception system, but we run another round of optimization, trying to find the optimal location to spoof those 60 points of point cloud, and such that it will be picked up by the LiDAR-based perception system as an additional obstacle. And we also show that with this kind of attack, it can create like emergency brake or freezing the ego vehicle at the intersection, since there's a spoof obstacles detected in front of it. And now that we can attack both LiDAR-based perception system and camera-based perception system, what's next? At that time, there's another module called multi-sensor fusion, which are essentially trying to unify the detected objects from LiDAR-based perception and camera-based perception. So many papers are also using these as a countermeasure for their attacks on either camera-based perception or LiDAR-based perception. So is it possible to like attack both pipelines at the same time? So what we're thinking about is devising an attack vector that can produce perturbation on both LiDAR point cloud and camera sensor. So what we think about is that we use this shape, like 3D geometry as the attack vector. For example, if you have a benign object, you can have a LiDAR point cloud pick up at the LiDAR and also camera image. But if you change the shape of it, obviously the 3D point cloud will change because the depth information is gonna change. And at the meantime, since the shape change, the shading and the texture can change, so the image will also change. And by using this attack vector and differentiate it, we can conduct the same optimization procedure to generate a special shape that can fool both LiDAR-based perception and camera-based perception. And we can skip the technical details. These are just like a quick demo showing that well, we 3D print this object and it's not being picked up in the AV, autonomous driving system. And these are just more example. You can see the cargo box are picked up and the pedestrian are picked up, but the 3D object are not. You can probably skip this one. And now that, okay, we show that, okay, we can kind of attack the perception system. What about the rest? Like we have prediction, planning, and control. So we think about another attack vector. Basically, in the real like driving scenario, you can control an agent and driving along a specific trajectory, for example, the red car. And then by such kind of perturbation, you can potentially fool the prediction system to think the yellow car is going to turning right with a slightly deeper curvature, and then potentially resulting in a collision of the plane. So yeah, so it's essentially the same procedure, but what we need to do is carefully formulating the attack vector or threat model into a mathematic formulation and then conducting the optimization. I will just skip the details. And as a result, you can see that basically in the benign case, it can do the correct prediction. And if we manipulate the trajectory a little, which is barely noticeable, it will be predicted incorrectly and resulting in a collision. Okay, so much about the attacks. So some quick takeaways. Obviously, ADS, it's not safe and secure, at least right now, it's not safe and secure. And this is due to the semantic richness really allows all sorts of different attack vectors for these adversarial attacks. And we can essentially using these adversarial attacks as a very effective proxy for generating unseen cases that the system fails. And actually, most of the threat model or attack vectors, if you design it like thoughtfully, it doesn't require an active attacker. For example, in the very beginning case, the sensor spoofing attack, we found that even between LiDAR itself, there will be like interference and also some ambient light. If it falls in the same frequency, it will cause similar patterns in the LiDAR point cloud without even an active attacker on the roadside. And also for these 3D objects, it's even more obvious. Basically, you can have this kind of rock on the road, and you can have a smashed traffic cone, which are not rarely seen in the States. And for the trajectory, it's even more straightforward. Sometimes there will be some crazy drivers on the road. You can never expect someone else to drive in cautiously. Okay. Yep.
Why does the two box work, but the irregular 3D printing they break both sensors?
Yeah, so I can go back to the slides, just seeing a bit. So essentially, we run this optimization with the target that it will not be detected by LiDAR based perception and camera-based perception. So these irregular shape of objects are specifically constructed through this optimization. Does that answer the question? That's good.
Yeah, thank you.
Let me jump back to the slides. Okay, with that, we are again entering into the second part. Like, how do we in return to improve the robustness of the autonomous driving systems using these adversarial methods? So what I think is that it actually serves as a very effective analysis tool for identifying design limitations. You can always get some insights from those adversarial examples you generated. And a few example. For example, the very beginning one, well, we are started to think after we like create the attack that can fool the lidar-based perception system so easily with so little amount of spoof points, we started to think why it will be identified as a vehicle which looks totally different. And as a result, it's actually the lidar-based perception model are not picking up this spatial information, or at least not picking up such information consistently. For example, if you take a look at the closer objects, it really, really dense. But if you look at the distant vehicle, it kind of looks like the sparse spoof points there. And also, if you look at the occluded vehicle, it's also kind of look like the spoof points, which are sparse and irregular. So what we concluded is that this model, since the supervision is only learned by mapping this point cloud at a local, at a specific location to a given bounding box, which is the supervision, such that it doesn't actually learn about the sparsity of the LiDAR point cloud is going to be more sparser at distant and denser at a closer position. So with all that domain knowledge, we can boil in that domain knowledge of this irregular sparsity of point cloud and try to enforce that the model can capture it, and as a defense mechanism. And also, we also conduct this analysis on what we find sometimes a multi-sensor fusion model are even more like vulnerable to adversarial attacks. And we found, for example, these frustum-based sensor fusion are using these cascading methods. Basically, you ask the camera-based perception to pick up a location of object at 2D and try to map it to 3D and cropping out the point cloud. And by using this cascading way, definitely you're exposing even though you are using multi sensor data, but the attacker only needs to attack the camera-based perception system. They can kind of override the entire system. And also for receptive field, it's similar. Basically, receptive field kind of represents how many like pixel information are used for the prediction. And since nowadays the model are getting larger and larger, and even recently when you have this attention transformer network, it's all connected. So it's kind of get a full receptive field whenever you have an input. And this will enable this remote patch attack. Basically, you don't even need to manipulate the target. For example, here, the vehicle, you can just put a patch on the road. You will remove the target obstacles from the perception system. Okay, and with that, it's pretty much showing that using these adversarial attacks, we are gaining a lot of insights. And also, I think fortunately, some of the insights are also adapted by the industry. For example, Tesla find that, okay, we mentioned due to semantic richness, that object detectors itself won't be good enough since you can using a closed-set object detector to rule it all. So Tesla, back in 2022, they developed this occupancy network to detecting occupancy instead of doing closed-set object detection, such that you can try to avoid open vocabulary obstacles on the road to get safer. Okay. And besides serving as an effective analysis tool, by generating all these adversarial examples, it's also a very efficient data augmentation for improving robustness. So There are so many different routines of how you can using this additional data to improve the model. For example, adversarial training is kind of treating as like min-max optimization, while you generating the adversarial examples in the inner loop and trying to optimize in the model in the outer loop. And at the same time, you can also try to find the optimal data augmentation using these adversarial methods to make the data augmentation more efficient. And we also have some work. I can quickly skipping this through. So what we did is that we built a defense against the trajectory attack on the prediction system, such that using the similar recipe of the attack, it won't work. I will skip this part. Okay. Okay, so a quick summary so far. What we have learned is that by having a perturbation generator, which are essentially from a attack vector and a data set. For example, you can have sense a spoofing attack, you can have specifically created 3D object shape, or you can have a specified trajectory, etc. You can get this perturbation generator. And with the adversarial optimization of these adversarial loss, which are usually a target like attack goal, for example, putting the perception system to not detecting an object or detecting a ghost object, or fooling the prediction system to think to predict the wrong trajectory, etc. You can construct these adversarial examples, which can serve as an effective proxy for generating unseen data, can use as a analysis tool to identify these design limitations, and also it can be used as augmentation to improving the robustness of the model. And now we kind of, in the recent years, we are transitioning from the classic stack of like small model, specialized model into this arrow foundation models is kind of like one model ruling it all. For example, at NVIDIA, we have these Cosmos, like a set of Cosmos World Foundation models, or WFMs, we call it. And specific to physical AI, we have two categories of model. One is physical AI synthesis. We have Cosmos Predict and Cosmos Transfer. Earlier, some of the simulation videos are come from this model. So this will being able to generating and synthesize photorealistic real-world data. And you kind of can think it as the attack vector in the perturbation generator. So we kind of have from previous specialized attack vector, we can have a very generic world model that can simulate in the entire world instead of focusing on very small details. And also for the data set, a quick analogy in the foundation model arrow is that it's related to the old experience you're experiencing. For example, retrieval methods are very popular in the early LLM stage. Basically, the LLM may not necessarily remembering all the data or all the experience you had before, but using retrieval system, you can quickly draw a similar context and prompting the foundation models to understand the scenario better. And similarly, this second category of physical AI understanding, for example, this Cosmos Reason model, it has really, really strong visual understanding and also reasoning capabilities that allows it to use common sense and reason like a human. And this is really the new, adversarial laws basically serving as a reward, kind of determining whether it's a safe or unsafe scenario. Is it good timing for me to do some special decision? What that pedestrian waving hands is trying to imply us. So yeah, so really in the era of foundation models, everything got transferred and everything got scaled up. So then with that as an intro, I will start the third part where we're trying to build this human-aligned ADS. Since with the foundation models, we are capable of doing so much more. We can start conquering the open vocabulary. We can have an initial human reasoning backbone model to like starting conquering the long tail without human in the loop. But let's begin with a bigger picture. For example, we have two kinds of work. One is this machinery, and one is human. So in the autonomous driving scenario, the ADS obviously is the machinery, and the human driver kind of represents how human will react. And in the real world, what we want is instead of building an ADS exactly like human driver, it's kind of difficult and maybe impossible because there are some fundamental difference between a machinery and a human. For example, machinery thinking more from a binary source, it's based on silicon, and human, it's a carbon animal. And based off that, there are definitely some like less overlap part from ADS and human driver. For example, if you take a look at the camera image, what human perceive is more on the semantic side. You pay attention to the color, to the shape, but for the machinery, they can tell very detailed difference since they are processing the numerical ones. Like they can tell whether that pixel level RGB is different, but human, you cannot. So there you go. We definitely want to have some overlapping between this machinery and human, such that we can understand the machinery or the autonomous driving systems more, such that the human driver can trust the ADS more to allow us to step into the world of fully automated driving. And in this section, I will briefly talking about two perspectives. One is how we use this human in the loop as a guidance to guiding the model we build to align better with human. And secondly, we are trying to use the model that already learns some human knowledge from text, just like LLM, VLM, multimodal language model as a bridge, since they can express a lot of things in text which human can understand, and we assume the model can understand from the large scale pre-training. Okay. Any questions so far?
When you say the human mind, we assume that there is someone in the car, but assume that we will be right now.
Yeah, so human line here is basically the ADS, the machinery here. It definitely can do something superhuman, right? For example, the reaction time, it's going to be superhuman. For example, the capability of processing all these sensor data on the numerical things, it's superhuman. But we want to build a system that human can fully trust and can understand. For example, when you have a level 4 autonomous vehicles driving on the road, you are also interacting, the machinery or the system is also interacting with other human drivers. So they have to have some interaction and understanding between how human drives and how like autonomous systems drives. For example, like a lot of like autonomous vehicles, we kind of have an impression is that they are super conservative. They're gonna stop at the intersection if there's busy traffic, right? That's kind of a stereotype right now, what we have for the machinery, but not necessarily the case in the future, right? Because we can change the machinery to be super aggressive, but what we need in the future at least for this fully autonomous driving, because you don't have human intervention anymore, is that we need to have some like agreement between how the machinery drives and how human drive, and how can they cooperate on the road in the same scenario.
I see. We basically, there are human drivers, there are machine drivers.
Yes.
We're not talking about self-being.
Yes. Yes. Okay. So, and let's first revisit the very beginning. We had this problem of hard testing, major detail long tail and dangerous scenarios. Pretty much we don't have it in the structure testing or real world replay, which are also crucial because you don't want any collisions or dangerous scenarios affecting the autonomous driving system's safety, right? And without such data, what we can do is we try to simulate it in the simulation. And to build such simulation, there are kind of two components. One is traffic model, which are essentially controlling all this behavioral interaction, like how would one agent react to a different agent and how it drive on the road. And second thing is renderer that turns all this word vectorized signal into the sensor data, like camera and LiDAR, etc. And fortunately, we have many tools in the renderer for the rendering purpose in the recent years, like nerve, and also Gaussian splatting, etc. We can pretty much realizing like photorealistic capability using generative models and also 3D reconstruction models. However, on the traffic model side, we are still a little bit behind. And one key problem of doing this traffic sim is the lack of nuances of realism for traffic modeling. So existing methods, a lot of them are learning from ground truth traffic scenarios. So as you can imagine, it pretty much doesn't cover any long tail, which means they don't have any negative examples. And also they are usually using these heuristic-based losses designed by human, trying to bake in some domain knowledge into the model, like collisions, off-road, etc. So, but sometimes these rules can be contradictory. For example, human drivers sometimes trying to avoid collision, they can go off-road or can go out of the lane. And also these kind of rules are really not easy to write and really, really hard to scale. Essentially, these heuristic-based losses will often fail to capture the nuances of realism. For example, here is the example I mentioned before by human examples balancing collisions versus driving off-road. So what we trying to propose here is using human preference as a proxy to do alignment and try to capture the nuances of realism in the traffic model. That is scalable to new scenarios and also traffic model agnostic. You can apply to any traffic model and also align with human knowledge. So a quick overview here is that we kind of construct three-stage framework. In the first stage, we're collecting human feedback by generating different traffic scenarios using a traffic model and ask the human to picking which one they prefer better. And then in the second stage, we are training a reward model by using these human feedbacks or preferences collected in the first stage. And in stage 3, we use the reward model as a guidance for human alignment when we train the traffic model. So here is just like a quick overview. Well, you are generating different scenarios and the human laborers will see, okay, it's an unrealistic stop at the intersection, they would just pass. And this one, just like crazy driving, No. And this one, the vehicle stop in the middle of the road, no. And this one seems all right. They pick this one. And these are kind of composed as pairs, which, well, one of them are most realistic. Sometimes the generated ones are like, all of them are not realistic. We just use the GT1 as the most realistic. And the worst ones, so we can construct like pairs. Well, D is more realistic than A, B, C. And using that, skip this. And using that, we can train a real-world model using this preference sample pair. And with such real-world model, we can supervise the traffic model. And as a result, we get much better to avoiding all these unrealistic behaviors. For example, vehicle stop in the middle of the road, or going off-road, ignoring the boundary. And sometimes you will go into the wrong lane. And with this traffic model behavior, we can combine with the rendering approach we mentioned earlier. For example, these are reconstructed by a nerve simulation. Basically, you can see this originally this vehicle stopped for sign, but in the reconstructed one, that one just rushing through the intersection.
These are visual, it's a real thing.
So the upper one is the camera log, which are collected, which is happening in the real world. The second row, is what we rendered from the traffic modeling plus the renderer we use. Here we use a nerve to like re-render the entire scenario. But you can also use in other stuff like Gaussian splatting or yeah. And secondly, we can also gaining like using human knowledge as a bridge, since right now we already have a suite of different LLM, VLMs that can interact with human, that we think, okay, that's more explainable than these detection bounding boxes, etc. So these are an old work from last year where we basically build a multimodal language model for driving scenarios specifically. And watch the demo. So essentially, with the language model, we define multiple tasks under scene understanding. For example, open vocabulary, object identification, road agent, semantic status, like blinking signal, or different ODD, like different weather and different ego agent behavior, and also prediction. And with the VLM and LM in the backbone, it allows us to create an agent that has human-like capability. Rapid learning adaptation through context, reflection, and error recovery. So for example, here you can, during QA, like interactive conversation with the agent to get better expandability, and both visual attributes and also behavioral attributes. And also it's capable of doing some simple reasoning, trying to understand what's the intention of such behavior. And these are an example of rapid learning by providing an in-context example to prompting that the snow on the road is dangerous, it can be slippery. And here also an example that like classic stack, you probably need a specialized model for detecting this right blinking turning signal. With a VLM, you can ask it to understand that this vehicle is going to turn it right. Okay, I think that's so much for the video. These are just like additional ODD. I can just skip that. Yep.
All this like scene understanding, this is happening in real time, like reasoning and
No, that one is not. This is purely a replay, so it's not real time yet. But yeah.
it's in the like training phase, you are doing the like reasoning and then.
Yeah, so right now it's more like captioning, like serving as an agent talking to, like interacting with human, but it's not serving as a policy that drives the car. And more recently, this year, we kind of extending from only using the VLM to show, okay, it has the capability to understand what happened in the real world or the driving traces. We use the VLM to serve as a safety evaluator. But a critical like challenge is that we don't have negative samples. So here, what we design is that we're leveraging the like semantic richness of text. For example, you can describe a behavior of an object with simple phrases like T-plan, decelerate, which we call it mad actions. And you can, by altering such mad actions and ask the VLM or LLM to inferring the future of the world, kind of serving as asking the LLM to serve as a word model to rolling out potential futures instead of actually generating all those detailed trajectories and sensor information. And these are actually more effective than generating a detailed future, since you're generating trajectory is going to be very detailed in dimension. Like two similar driving decision can result into very different trajectories, but two different trajectories can be falling into the same decision. And we usually, for human driver, we usually paying more attention to decision level differences instead of trajectory motion planning level stuff. And by this method, we can generate it about like a set of like unsafe scenarios from a safe data set, which is new scenes. And we using this generated counterfactual data to train the VLM to getting better idea of how unsafe scenario should be look like. And as a result, you can see it can actually generalize onto unseen scenarios. These are from Waymo. You saw that pedestrian, the cyclists are leaning forward to the road, which definitely is unsafe. And this is another benchmark where they collect a bunch of scenarios where collision happen. And we use it to test our system that can detecting the unsafe behaviors. And there are more examples. And with such like safety evaluator one, there are like many things we can do. First, we can do like data curation, trying to find out like less safe scenarios and trying to enhance the model performance on those scenarios. And also we can directly use this evaluator as a verifier on policy during the inference time to reject sampling all those bad behaviors, such that natively without training the driving policy, you get a safer model. So for example, here, the original trajectory predicted by UniAD ends up a crash. But what we did is we sample multiple trajectories from UniAD, and we run our evaluator on top of it and select the safer modality, such that we can filter out the unsafe trajectories. Okay. And with that, I think it concludes today's presentation. In the first two parts, we talk about how these adversarial attacks happened on the classic ADS and how we can improve in the robustness by using it as a analysis tool to getting insights or use it as an efficient data augmentation. And in this last part, we're talking about how can we build this human-like ADS in the foundation model era. Well, we have more powerful model, but also less expandable. All right. And I think we're just right on time. Yes. Yeah, that example is used for showing the, like LLM backbone, they have these self-correction capabilities. Yeah, basically they have these reflection and error recovery capabilities. So originally the detection for the right blinker is wrong. And with a human ask like a reflection, the model can get the correct answer. You can think it as I think these are actually before like DeepSeek stuff, like last year. So, like when this DeepSeek coming, they have a lot of like, wait, I did something wrong. I should redo it. That thinking process is exactly the same thing, like reflection and error correction. So through this thinking process, they can get a better answer.
This is a good question. We use the large model, not the distribution model. So we know the average hallucination. So I mean, solution or consideration design choice.
Exactly. I think hallucination or like generally you can kind of referring these to classic like precision and recall issues, right? So for hallucination, it's more like a lot of like false positive examples, and at the same time, it can also have false negative or the model neglect some critical components. So that's also one critical direction we need to like improve before we put this on the system. What we did, I didn't show the slides here, but what we did is using human in the loop, trying to correcting or align the model better with human preference. For example, critical components you shouldn't be missing, should be added back to the label. And then we can run another round of visual grounding pre-training to let the model better align with the human on the task.
We have put the experts into the
Yes. Yes. Essentially, like right now, I think there are some limitation of the foundation models or VLM LLMs. But sometimes there are also issues with synthetic data. So for VLM LLM, it can help generating this lower quality synthetic data, which can help with the pre-training or SFT. I mean, even there might be some errors, which is the same case for LLM training, right? You are crawling from open world, like web scale data. You cannot verify all the high quality of the data, but we can have this hierarchy structure of, we have high quality data, but doesn't scale that much. We have medium quality data, but we might be using the high quality data to do evaluation, testing, using medium quality data to do SFT, and some low quality data use it for pre-training, such that we still have like a quality assurance for the final model.
Final question is, seems like from NVIDIA's vision, the large language model can become the trend, right? As well, everything will be. Previously, we have different stages right now, just different places with one model. So
That's good.
as well.
Yeah, anyway, let's go ahead and ask him here.
Yeah. What's your vision?
Yeah, we're not replacing the entire classic stack. It's because for the classic stack, like perception, prediction, planning, and control, you do get some like additional benefits from it, right? Because you get some explicit intermediate representation, for example, bounding boxes, even though that doesn't scale to long tail that much. For example, open vocabulary detection is really hard to achieve by using object detection. But we still keep that pipeline because that helps us to ensure the safety or as a failure guardrail. And these like large language model, like LLM as a backbone, which are more often used for conquering the long tail scenarios that's not seen in the real world. But that can be maybe 10% or 1%. As we are rolling out, we probably get more data and more experience how to handle it.
So I have two questions. The one is, you guys, since NVIDIA doing a lot of hardware systems on vehicles, right? So